Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we will be looking at curve fitting, and specifically we will be developing the equations for fitting a straight line using linear regression. So the concept is that we have a set of data, and what we're looking for is a mathematical definition that we can use in future problems. So we would like a way to approximate the function for our data. Let's assume what form that function will be. So in this case, we're going to assume that it's a straight line fit, y equals mx plus b. And our goal is to find the values of m and b that are the best fit to the data. Now the problem with this is defining what we mean by best fit. There's not going to be a set of parameters that works for every single point in your data set. I mean, well, it's unlikely at least. So what we're looking for is the best. One way to define this is the one that creates the smallest set of error values. And we're looking for all of the errors to be as small as possible at once. So one thing that we're going to need to do is just make sure that we quantify them all as positive. One way to do this would be absolute value, but another that works very well is to take the square of the errors. And if we add up all of the square of the errors, then we're going to get the sum of the squared errors. And this is like one giant error function. And our goal should be to minimize this sum of squared errors. So let's consider that we have a data set that's in the form xi, yi, and we're looking to fit it to the model y equals mx plus b. So we can estimate the deviation or error for each individual point as the estimate mx plus b minus the measured y. So our estimated y minus the measured y. And if we do this for all n of our data points and add them up, but making sure they're positive, so I'm going to add up the deviation squared, I end up with this expression. And what we want to do is find the value of m and the value of b that minimize this. We're going to use calculus rules to figure out what our minimum value is. And so we want to find where the derivative of this e function with respect to my parameters m and with respect to my parameter b, where those are equal to 0. And we, of course, could check a second derivative test to make sure that these are a minimum. It's not really going to be necessary in this particular case, but yes, we can do that too. What this is going to do is for each partial derivative of e with respect to a parameter, I get an equation. And in this case, I have two parameters, m and b. And so I can solve this system with two equations, two unknowns. But I could do this for any function. It doesn't have to be just for y equals mx plus b. All I need to do is put in my functional description minus the measured value, square that, and take the derivative with respect to each of the parameters that I'm trying to fit. So let's see how this is used. First, let's take advantage of a couple of, well, one is a notational simplification and the other are some calculus rules. So the first, notationally, instead of putting the sum over all of my terms from I equals 1 to n, I'm going to suppress that and just put a summation sign, and that means I'm adding up all n of my terms. Second, in my calculus rules here, I have that the derivative of a sum of terms is equal to the sum of the derivative of each of those terms. And the second rule is the chain rule for something squared is 2 times that something times the derivative of that something. So if I do that for our little linear equation, then what I end up with is this. So the derivative of the sum of the deviation squared with respect to parameter m first. And we can take the derivative of each term, so 2 times mx plus b minus y times x. That's the derivative of this inside piece with respect to variable m. And I'm going to add this up for all n of my terms. And if I just rearrange this, because the 2, I can divide everything out, and I can take the sum of each piece individually, I end up with this. So m times this grouping plus b times this grouping is this. So m times the sum of all of my x's squared, and then add them up, b times the sum of just my x's, is equal to the sum of the products of x and y. Let's do this for the parameter b. So dE dB. Same first step, bring the sum outside of the derivative. And then now that I'm going to take the derivative, so it's going to be 2 times this inside group times the derivative of this with respect to b, and I end up with this expression. Again, divide through by 2. And what I see is that m times the sum of my x's plus b times the sum of a bunch of 1's. Okay, if I have n 1's added together, it's just n. And that's equal to the sum of my y's. I'm going to combine that with my previous equation, and I have 2 equations with 2 unknowns. So I solve this for m and for b. Here you can see that m, or our slope, is, well, okay. I've changed the notation a little bit because this is a convenient and typical way this is written. This bracket indicates that I'm taking an average, which means that I add up all of the x, y's and divide by n. Now, so the average of my x, y's minus the average of my x's times the average of my y's divided by the average of x squared, so I have to square each term and then add them up, minus the average x quantity squared. So I average the x's and then square that answer. And b is the product of the average x squared times the average y minus the average xy times the average of x over the same denominator. And again, these things are written here. And you can go back and compare the two. Basically, there's a lot of divide by n to get to this form. So if you were looking at this in terms of an algorithm, basically just simply you're going to choose the model that you want to fit to the data. You're going to derive the set of equations based on the minimization criteria, and then develop the matrix form AX equals B, and then solve the matrix system, and that will get you your parameters. So the steps are fairly simple. We're going to look at an example in our next video lesson. Thank you very much for your time.